Well, hello everyone, and welcome to MacDermid Enthone's discussion on the decorative acid copper processes. My name is Robert Collin. I am the Americas Technical Manager and will be the moderator for this event today. The presenter, Chrissy Polera, is the Decorative Business Development and Product Manager for Decorative Coatings. For the questions you have, please submit them during this webinar, and we will answer them via email upon the conclusion of this webinar. And again, thank you all for taking the time to learn about MacDermid Enthone's decorative acid copper processes. And Chrissy, with that, this session is yours.
Thank you, Rob, and thank you everyone for joining me today. I would like to start by giving some background on copper, why it's important in a plated system. Then we'll talk about some of the processes that are involved and talk about the acid copper specifically. So why do we need acid copper? What is the benefit of having acid copper in that plated construction layer? If we think about the benefits that it adds, and I look at a final part, a part that comes off the line or that's on a vehicle, for example, that brightness, that luster, that highly leveled surface, that comes from the acid copper. It really plays a huge role in what that final plated finish looks like. Another important attribute of the acid copper layer is that it's really a buffer for stress. So I have a plastic substrate, I have a lot of copper, and then I have nickel metal layers. If I don't have that copper in between my substrate and my nickels, if I have some quick changes in temperature, I could have some stress issues, some cracking. We don't want that plated deposit to essentially pop off the substrate. So that's the function, another function of the acid copper is to really buffer it. It's a very ductile deposit. So it allows some expansion and contraction of that part and still allows that plated layer to remain intact. When we think about what we want our acid copper process to be able to do, some general requirements here. So it needs to be bright across the entire current density range. So obviously in the highs, but with more complex geometries that are out there now, we might need it to get into the lows pretty well also. We need it to level across that entire part. Again, we need that ductility to prevent any issues with stress or cracking. And obviously we want to have our defects and rejects at a minimum. So this is just an example of what a cross section of a copper plated part would look like. So we have our plastic substrate followed by an electroless layer, typically electroless nickel. We have a copper strike over that to start to build some copper thickness, provide some conductivity. And then I have my copper, in this case, a triple nickel construction, and then my chrome layer. So this is a dramatization, obviously, but you can see that, the substrate itself after the etch is not smoothed out at all. The electrolysis just fills into those holes that have been etched out. The copper strike starts to level it out a little bit, but really it's the copper, and again, dramatized, but it really is the copper here that starts to level out my plated surface. In this case, 25 microns in this cross-section representation, typical of an exterior automotive OEM requirement. So what are the market drivers for technology for acid copper? Why do we need to continue to develop these processes? What do we need them to be able to do? And how does the market drive that? How does it dictate these advances in technology? If we think going back, say even 10, 15 years, part geometries were simpler. So I really didn't need to worry about throwing into severely low current density areas. I had a limited range of articles, so not a whole range of parts to worry about. The testing requirements were for sure a lot simpler, and I had some poor molding quality issues to deal with. If I fast forward to today, the geometries that we're seeing on these parts are much more complicated. Drastic differences between high and low current density areas, a lot of more parts to deal with, lots of different types of articles we're talking about. Those testing requirements have increased dramatically, and we'll talk about some of those specifically and how they relate to copper, and some improvements in molding quality. So all of these are really driving us to develop a more robust and technologically advanced process. So at the OEM level, the copper thickness requirements have increased, and I speak specifically here about automotive OEMs. There are new specifications out there that are requiring more rigorous testing, extra thermal cycles, for example, to be able to be a true representation of how these parts are going to perform in the field. So we're requiring more thermal cycle results, more cycles to be completed without failure. We also, or the OEMs are also requiring a reduction in the stress of these plated parts. So how do we accomplish this within our plated layers? And what challenges do those requirements represent to the applicator, to the supplier? So if I'm mandating an increase in copper thickness to really help with thermal cycle and with these stress requirements, how do I, at the applicator level, increase my thickness without slowing down the production on my line? Still being able to run the same amount of bars per hour or bars per day without having to increase my plating time, for example. So there's a significant increase in current density here, which becomes complicated because we know how sensitive some of these systems can be. If I even try to increase from 25 to 30, I might see burning. So now I have to add some extra shielding to my rack to eliminate that and to be able to even out the thickness distribution across the part at a higher thickness without burning with the same amount of production. Challenges for sure. So how do we as a chemical supplier step up and help to eliminate or make these issues less onerous on the suppliers and the applicators? So I would like to introduce you to our copper portfolio. There are a few systems that I'll be discussing today. The CUPROSTAR system is what will be highlighted mostly, and that's what we typically use for plating on plastics. Our QMAC copper systems are typically utilized on metal. I say typically because there are circumstances where they are flip-flopped and interchanged, and obviously every situation and application is different. So it's not cookie cutter. We determine which system is best based on the application and the requirements. But these are our processes that I'll be talking about today. Copper strike, which we saw in our layer construction in that cross-section representation. We have that copper strike after the electroless layer for plating on plastics, then followed by one of our acid coppers, whether it's the 1600 or the 1610 from the CUPROSTAR family, and we'll talk about those in a lot of detail today, dye-based and dye-free systems that are offered. And then the QMAC Optima process, which is typically, again, used for metal plating, but can also be utilized for plastic in some special cases. Our copper strike, which I'll touch on briefly, again, is the CUPROSTAR 594, utilized in a plastic plating layer after the electroless nickel. Highly conductive, so really allows for us to plate a good base layer for acid copper. We're able to build up the acid copper after this strike. We get good coverage from this system, good throwing power, and we don't need to rinse after the 594 going into the acid copper. Whether it's one of the CUPROSTAR systems or the QMAC, we can go straight from the 594 into our acid copper bath. So again, the strike is utilized for plating on plastics after I plate my electroless layer. And then we get to the acid copper, which is really the focus of my talk today, specifically highlighting these two processes, the 1600 and the 1610. The CUPROSTAR 1600 is our dye process. It has adjustable leveling, and it's excellent. So we can maintain this process very easily and get very acceptable leveling across the entire current density range. The throwing power is excellent, and I reduce the amount of pits and pores that are in the process. We know with acid copper, that's one of the main concerns is pitting and pores. So really, that was one of our focuses when developing both the CUPROSTAR 1600 and the 1610. The 1610 as a dye-free process is even more beneficial for pit and pore reduction because it's so clean. I don't have the sludge in the tank. I have very clean tank walls, very clean anode bags because of the absence of that dye. I have good leveling with this system as well. No concerns for over leveling, excellent throwing power, and lower risk for flames as well. So again, complex plastic parts typically, which are prone to over leveling or flame patterns, that's where we typically find that the CUPROSTAR systems provide the biggest benefit. And then again, the QMAC Optima, this is a dye system, but it is very robust. It's really beneficial when we're talking about really complex metal geometries, really trying to throw and get brightness and leveling in those low current density areas. We have superior brightness in the lows with the Optima process. So again, typically used for metal, but we can utilize it on plastic depending on the application. So I'd like to take some time to talk to you about the 1600, the 1610. I'll show you some examples of these processes in production, some of the benefits that we've been able to achieve by switching customers from other processes to these ones. So again, it is promoted heavily for plastic, but we can utilize it for steel, brass, aluminum, and zinc die cast. It's ideal really when I need high leveling, excellent brightness, and throwing power. So I have a customer, actually, we have a customer that is utilizing this process on aluminum for wheels. So we think about really needing great leveling, especially in the lows, being able to throw into those lows. We've been able to do this very well with the CUPROSTAR 1600 process. Again, high tolerance to pores, and really won't burn in those high current density areas. And so that's one of the challenges. Again, we talked about pushing these systems so they can get into those low current density areas without burning in the highs. The thickness distribution on these systems is exceptional and allows for us to be able to do that. I can adjust the leveling for as much or as little as I need to. So you can imagine for a metal part, I would need more leveling than I would for a plastic part. I have low tendency to pit and generate pores in this process. Because of that, I can run at a lower air agitation. So if you are walking a line, typically when you see an acid copper bath, that thing is moving. There's a lot of air agitation to reduce the amount of pits that form on the surface. I don't need to have it as that air turned up as high with these systems. And I can still get the brightness and leveling that I need even in those low current density areas. As I indicated, that thickness distribution is improved compared to typical processes. And I can even utilize this system for direct plate in addition to conventional plating on plastics. Minimum defect rates, obviously, those are a goal when we're developing new processes, not sensitive to over leveling, and it's very easy to control. These are the products that make up the CUPROSTAR 1600 process. So for makeup, I'm utilizing 3 components: a makeup, a maintenance A, and a maintenance B. I use the A and the B also for maintenance, and I have 4 other service tools that I can utilize for the system: an enhancer, a leveler, a wetting agent, and a carrier. All of these can be mixed together. So when I'm talking about maintaining the system, dosing systems, I can use the maintenance A, the enhancer, leveler, wetting agent, and carrier can be combined in those feeders. So I don't need to have 6 different feeders for my system. I can utilize only 2 between combining the A with the service tools and then having the maintenance B on its own. (1610), again, as I indicated, is my dye-free process. Good leveling, no over leveling with this. One of the biggest benefits, though, that we've seen with this is the reduction in sludge formation. So because of the absence of that dye, I don't generate sludge. I have very clean tank walls and anode bags, which dramatically reduces my need for carbon filtration and reduces my risk of pitting. I still have excellent throwing power with this system, and I do have reduced risk for flame patterns as well. These are the products that make up the CUPROSTAR 1610 process. So I have my carrier, brightener, leveler, wetter, and replenisher. In this system, I am able to combine my carrier and brightener together in the feed. If leveler, wetter, and replenisher are needed, they can either be added via dosing or over the side. The function of these additives, and this is pretty generic. Anybody that runs an acid copper process, I think, would see that these are providing the same benefits as others. Grain refiner, benefit for that carrier component, especially in the high current density area. Also improves the dissolution of my anodes. My enhancer or brightener component, depending on which system I'm talking about, really gives me that general brightness across the entire part, across that entire current density range. Helps to reduce my surface tension, which aids in pitting reduction as well. Leveler component, pretty straightforward, just aids in leveling that part, that surface. And then my wetting agent further improves that surface tension, allows for reduced air agitation, and reduces pitting as well. So these systems are running in production, not just here in the Americas, but all over the world. So I wanted to give you, show you some pictures of some of the advantages of the CUPROSTAR 1600 and 1610 versus some of the other processes that it's replaced. In this case, we're able to avoid effects of over leveling. So this is a system that is not, this is a part that does not have the CUPROSTAR copper layer underneath it. You can see some over leveling defects here. By utilizing the CUPROSTAR 1600 or 1610, I'm able to avoid those over leveling issues. We talked about thickness distribution and how important it is to be able to have thickness in the lows as well as the highs, without overplating the highs, burning the highs, and still having a sufficient amount of thickness in those low current density areas. It's hard to do with acid copper, or can be, depending on the process. We have two different situations here to highlight. One, because of that advanced thickness distribution of these processes, we're able to see less cracks after converting to CUPROSTAR, as shown in that first photo, and again, less burning after converting to CUPROSTAR in that second photo from that second customer. So that thickness distribution really is key to being able to operate without defects and really opening up that operating range. Some robustness examples from my CUPROSTAR 1600. We want to make sure that when we develop these systems, our goal is to be able to develop a process that is customer friendly and that really allows for a wider operating range. We know accidents happen. We know feeders get overfed. We know some people over add to the tank. We know sometimes they forget to add to the tank or the feeders aren't working at all. So when we're developing these types of processes, obviously, we're aiming to have them run at best practice in every situation, but what happens if they don't? So these are three different examples of situations that were either overdosed or underdosed. The first was an overdosing of the maintenance A in the CUPROSTAR 1600. So an equipment error where it allowed or forced the maintenance A to be overdosed into the system. We were not, thankfully, subject to an increase in reject rate. There were some temporarily effects of overleveling, but the reject rate did not skyrocket or go up as a result of this overdosing. In the second scenario, we had a 20x overdosing of the maintenance B. There was an over add. So we needed to filter it out. We had to do carbon filtration twice during an overnight shift, during a third shift. But we were able to reestablish the performance of the bath very quickly by doing that. And the third situation was an underdosing. Basically, the dosing pumps were off. There was a malfunction in the equipment, and they were not dosing any chemistry into the system for 24 hours. And even as a result of that, we did not see any increase in the reject rate. So again, it's something we strive for, and we're developing these systems, is to try to minimize the amount of rejects and errors that take place, even if the bath is not running exactly the way it should be. Here's some example of brightness. I highlighted how bright these deposits can be for both the 1600 and the 1610. You see the two parts that are displayed here on the top are a little bit duller. This was an acid copper at a customer that was replaced by the CUPROSTAR underneath it. And you can see in both cases, on both of those surfaces, that they are brighter than the comparative parts. So again, very bright deposit, nothing, no major changes in the feed rates or the temperatures of those systems, just run under standard conditions. Leveling, obviously, is something that we strive to achieve with copper. Here in the existing or the replacement acid copper, we saw a lack of leveling on these parts. For the 1600 and 1610 replacement, we saw no over leveling of parts. You could see nice bright level without over leveling in this situation. And pitting, which we know was a huge concern. Some pitting in the photo on the left, but after switching to the 1600 and 1610 processes, no issues with pitting on those parts. Edge effects can also be an issue. Sometimes we have sharp corners, 90-degree angles. They're not ideal by any stretch, but sometimes we cannot avoid them. Here you see that even after 3 hours of plating in the acid copper, we don't see any edge effects with the CUPROSTAR system. So I wanted to share a case study with you, and this was done a few years back now at this point, with a large POP plater here in the Americas, automotive supplier of interior and exterior trim. We had the opportunity to test our 1610 process, and some of the issues that they were having, some of the limitations of their previous process, were that the line was configured for only for them to be able to build a copper thickness of 15 to 20 microns. Obviously, we talked about the fact that OEMs are requiring thicker copper deposits to help push these OEM requirements and OEM performance requirements to the new desired level. So how do I get this new thickness requirement without sacrificing production and efficiency? Whenever they tried to increase the current density to get that thickness, they had a lot of burning issues. If they tried to increase the temperature to increase that thickness, they found that they had a large brightener usage. They were also not able to analyze the system that was in place at that point, and they were carbon filtering continuously based on the need or their usage of auxiliary anodes. So a lot of issues that we were asked to help them overcome by installing the CUPROSTAR 1610 process. Again, auxiliary anodes, so pretty much worst case scenario. We were able to run the auxiliary anodes. We were able to run the bath at a higher temperature, so up to 86 in their case, Fahrenheit, without seeing an extreme increase in additive usage. We also didn't experience any loss of leveling and any brightness when we did that. We were able to bump their current density up from 25 to 40 amps per square foot without having burning in the high current density areas. We eliminated their need for continuous carbon, and they have seen a lot less maintenance. So, I indicated the tank walls are a lot cleaner. The anode bags are a lot cleaner. So they were able to really reduce the amount of maintenance and cleaning that needed to be done on the system. One of the advantages of the CUPROSTAR family, the 1600 to the 1610, is that I can easily go from the dye-free to the dye system. They're the same base chemistry. So I know there's a lot of people out there that have said, oh, I need to use dye. There's no way that I can plate these parts that I have without a dye, and it's just not feasible. And what the 1610 and 1600 allow you to do is to try, if you really are having issues with pits and a dirty tank walls and anode bags and really having to run carbon continuously, trying the 1610 is really such a low risk, because if it doesn't work, I can easily just add the dye to that system, and it essentially becomes the CUPROSTAR 1600. So there's a lot of flexibility in there to see if it works based on the application. Another one of the tasks that we were asked to meet was analysis. So we were able to control the additives by analysis. We were also able to analyze the breakdown products by HPLC. So a lot of benefits that we were able to bring to that customer just by switching from their existing system to the CUPROSTAR 1610. Before we close, I just want to highlight some of the attributes of each of these systems. Again, the CUPROSTAR 1600, that is the dye process. It was developed for plating large plastic parts. It can be utilized for direct metallization in addition to conventional POP. I have a very low tendency to stardust or pit. I can get excellent brightness and throwing power across the entire current density range of that part, even in the lows. And I'm able to adjust that leveling so I don't have really any tendency to over level the deposit. And then that 1610 process, I can utilize this in combination with auxiliary anodes, as we saw in our case study. Reduces my concentration of breakdown products that we know have a tendency to form when auxiliary anodes are implemented into a system. I don't need to utilize carbon filtration compared to those dye systems. I can analyze all the additives and the breakdown, and I can really push the temperature of this system. I know we said 86 for that specific case study. We've had others push it further into the 95 to 105 degree Fahrenheit range. So a lot of flexibility with this process to still achieve exceptional results. And these are being used worldwide. This isn't just a lab clean process. It's being utilized at several customers here in the Americas. It is well known and accepted technology at this point. It's been on the market for several years. It's globally available. So it can be manufactured in any of our facilities around the globe. So when we talk about, OEMs are looking at a globally viable process that apps this process, whether the CUPROSTAR 1600 or 1610, those absolutely fill that requirement at the OEM level. We have a high level of expertise now since we've been running them in production for so long. Again, not just here in the Americas, but in Asia and Europe as well. And I know I talked a lot about automotive in here, but these are being used in every industry segment. So building and hardware, sanitary, plumbing, and others. So there really is a lot to offer any industry by utilizing our CUPROSTAR 1600 and 1610 processes. With that, I'd like to thank you for your time today. I hope you're all staying safe and healthy, and please enjoy the rest of your day. Take care and thank you.
Thanks, Chrissy. Great informative session on our decorative acid copper processes offered. And again, please contact Chrissy Polero directly for any questions you think of once this webinar ends. For those of you that have typed in questions, we will get back to you via email. And again, thank you very much, everyone, for joining this webinar. Have a great day, and please stay safe.